right, this is totally the beginning of the lesson. There is nothing that was said prior to this recording. As a matter of fact, the universe didn't exist prior to this recording, so this is it. Good luck. All right. So, force, electric, physical energy is the potential to do work, aka the potential to, let's put this guy right back here and go, hey, what's probably going to happen? That number is probably going to decrease because those are, cool, that's going to do that because it was put in this. Yes? All right. What?
They don't have any context.
I know.
I don't know. What do you mean context of what? There was nothing before this particular recording. I just started talking in the middle, and as soon as everybody knows what I'm talking about. All right.
Well,
Now,
they can't see your
this.
voice and writing that.
Yeah, you're not writing
They
it on
don't see your invisible.
keyboard. They can't.
Because you get kind of whiny. You get all familiar and whatnot, so you guys get whiny. All right. So, this guy, what do we expect those to do? Repel.
Oh, wait. Oh, sorry. I was.
Okay. This guy says if we put something here, it's going to repel.
Yeah.
Okay? Or a negative and attract. Okay? This guy, what are those going to do? Repel. And when they repel, what does this do? Decreases. It's a scalar way of addressing this thing right up here at the top. The other nice thing about energy is once we combine it with conservation of energy, if we know how much this decreases, if we know how much of that's used, we can take that number and apply it to other types of energy, like heat or motion or light and sound, aka literally what you're looking at right now, that runs on electrical energy powered by that guy over there at 120 volts and runs through here, putting out its energy in the form of light and sound. Okay, that's ultimately what this is going. Now, why would we use this instead? Well, we use that instead because do we technically know what's going to go from there to there? Do we know how much charge is going to go from there to there? No. So we say that, hey, between these two spots is, well, actually, let's use the number I just said a second ago, is 120 volts, which says that between those two spots, if the charge moves from here to here, that it will get 120 joules for every 1 coulomb that passes through it. Does that make sense? Or, like I said, it's an empty hill. Okay? Now, the purpose of a circuit is really just simply to control that energy. Okay? So, what do we need? What do we need on the empty hill? Go running through the voltage in order to get energy out. We need children, charge, yes, absolutely. We need coulombs, all those C words, okay? And so we need to have children, coulombs, charge, passing through, and we get energy out. But here's the thing, as it pertains to this guy simply up here. Does it keep running?
No.
Is the computer currently running and has been running the entire time? What do you mean, whoa, whoa, whoa?
Yes,
You're wrong. Suck it up and deal, child. Woo.
The question.
Very wrongly. Everyone laughed at you immediately. It wasn't just on me. All right, moving on. So it's regularly, it's not putting out one child, okay, and just saying, hey, this is energy. Otherwise, it'll turn off, turn on, turn on, turn off, and then be done. So we need to continuously put out children, right? Or charge. We need to put charge through the system. Fair enough. So we need to put that through, and if we need to continuously do it, we should probably compare this to... No. When we have a number that is continuously changing, what variable should we regularly compare? So, for example, if I just wanted to talk about distance, right? Spanauer just walked 5 feet. But if Spanauer starts continuously walking, it makes more sense not to talk about how far he's gone, but how far he's gone relative to what? Time. So, if we keep having children roll down the hill, we should probably compare how much they do to time. Yes? How many children per second? And combining these two together, which we'll see a little bit later, I can get how much energy I put out per second, which in the case of this view board, where's it at? Oh, it's almost always written on here. Where are you at? 4.5. Okay. This bad boy runs on 540 watts, which means 540 joules per second. Now we know that it's coming from that outlet over there, so we're getting 120 of those joules per coulomb, which means 1 coulomb is going to get me 122 is going to get me 240, 3 is going to get me, of course, 360, another is going to get me 5, so I'm going to need about 4.5 coulombs per second running through this particular guy, and yes, that is actually relatively reasonable for an electronics thing of this particular size. Here's another way to say it, okay? I'm going to draw a circuit for you, a very basic circuit. Here it is. You know what? No. We're going to do a small lap.
Oh my god. Do not.
No.
If you can't do this lab, I will agree with you. All of you are going to come up, just one set per group. Let's actually, Isaiah, since you're very suffering now, let's just join one of these two tables. Pick the dealer's choice. Okay, have one person come up and grab 3 items. 1 battery, 1
you are literally like
EMC light bulb, and 1 wire.
If we can't do this, it's over. Lock in.
All right.
Material.
You are attempting to find 4 ways that the light bulb will light.
Ada, you would do terrible.
1 battery, 1 wire, 1 light bulb. That's it.
4 ways to make it. Alright, so we gotta get current, we gotta get those electrons flowing through that thing.
Yeah.
Doesn't even fit my binder. Yeah.
Alright,
I'm not battery. I think we might be.
Okay.
Now let me be clear, so we can protect Brianna's personal emotional health. I am not saying to do this lab you're going to get it perfectly. I am saying that to do this lab you just have to try it. Just keep trying. That's it. And if you don't get it, keep trying. I will tell you that usually I have done this lab at every single level that I possibly teach. Doesn't matter the level. Usually within 5 minutes, somebody yells in irritation, "Your stuff's broke." Nope, it's probably you. All right. So off you go.
There's not like
Okay. So we have
what?
right now.
Did you get a shot? I didn't get any shots, so it should be fine.
If the wire is hot, you're getting a flow of electricity, just not in the right spot, and stop what you're doing. You shouldn't be in danger. If the wire gets hot, you have a flow of electricity, just not where it's supposed to be.
Yeah, on the wire.
Or what if you have the wire connected to one that you have it connected to yourself? Could you just be the flow?
Yeah, wait.
Ow! It just
Oh, yeah. Wait, no, here. Guys, I'm serious. Got it. You're
What if you move
Here, wait,
the light
can I
bulb
see it?
while touching this?
Because it's not the circuit.
Like, what if you rub it on the
Hello?
wire?
You gotta squeeze the juice out like a lemon. Warm the battery up.
So I would think that if I held that there.
Maybe.
This actually. I'm shocked.
Are you really shocked? Because you should stop doing that electricity-wise. That's good.
Honestly, I think
Expand our stuff.
I want it to be. Let's check the voltage on this battery.
So we have the battery, right? And then if we'll touch both of them,
This is
like,
yeah.
it would polarize it, right?
I think it's 2.5 volts. This is 1.5 volts. I think it's
The wire
so
doesn't feel hot.
Okay, the positives are going to the negative side, right? This is the positive. Oh, wait, no, the negatives are. So.
This makes me
I feel like this is a red herring.
Like,
Who needs a battery? I feel like this
I
is a
really
red
wish I
herring.
had a prop right now that could be like, "You think
That's red.
What is that? Are you?
This is a red herring.
You can drop
I'm
it
gonna
in.
I'm gonna get a red herring.
Like, just how am I supposed to suspend this battery?
We're done.
That's a
avoiding
spade.
shopping.
Is it? Here, but
What?
if I'm.
I know, I'm gonna.
Your best.
An hour. I'm gonna find this.
That is
I'm
not.
gonna show it to him.
Like, that's not gonna work.
You need to
Oh.
see that.
I'm
I'm gonna be starting doing this last time I talk about this.
No, it's not gonna.
Was it? Here it is.
Wait, you can't.
This is why I hate labs.
I think we'll do
Hold it in place, Nate. We got this.
Yeah, don't cheat over there.
I want another wire.
Can we try it with 2 wires and then not count it?
Wait. Oh, you did? I think our wires.
It needs a reason to travel to the light bulb instead of just going straight
Yeah,
to
there's
the
no
light.
dent.
I think that's
probably
better.
why.
Wrap this around.
You should do it because it's
I know, and I'm trying.
I gave it a reason.
It works.
Oh, what did they do?
Okay.
I will happily check any of yours, just not in front of you.
Hold it again. Hold it
Wait,
again.
will you check ours?
Okay, the electron is playing this way, so I feel like
Should we
want
double
to check yours.
Yeah.
Check to see yours.
I think it.
Okay.
I'm currently cheating.
I'm not cheating.
Well, I like
But we needed to actually.
going in there and watching you do it.
There's just no
What
shot.
other
Okay,
one?
he did it really quick, right? So it's gonna happen.
Yours actually is broken.
Can you
Oh,
test
great.
ours? This has to be.
Settle.
Yeah.
Yeah.
Stay. Let me get a new line.
Maybe
Hold on one end.
I mean, our wire does.
I see no reason
Oh,
to
wait,
do that.
and then turn it to the other side of it.
These
This is a
these
joke.
electrons are like pulling it.
Yeah, I feel like everyone else will be trying this and nobody else is getting it.
Wait, so it is working?
Do the deal.
It was just like,
Would you like to test ours as well?
maybe there needs to be an actual connection.
Okay, we gotta do that. So we have batteries,
Never-
right?
They never really
Yeah.
has it.
As long as it's 100.
Oh, you're
Oh,
kidding.
what?
It's that
Did you
easy.
get-
You took that one time.
So it's
Do
hot.
not look up the answer.
Oh,
Okay, the other side.
Of anything that you do in here, that will piss me off the most.
Wait. It's gone now.
Is it hot?
It was lighting up the, what?
You gotta be able to do it on purpose.
Okay, you hold the light bulb. And
Yeah.
and then
He's
doing the wire.
Maybe we
Okay, guys.
do we need to wrap it? Oh, wait.
Yeah.
Maybe we need to.
There we go.
Is it?
Yeah.
It's not good, but we did it.
Maybe we need to wrap like
The
the
end of this on the positive.
Doesn't want to
wrap
Light
like
bulb.
this
The
around
light bulb's temporary. We got it.
the bowl.
There.
Yeah,
How are
it's,
you?
it's
gonna
steady.
do it?
We,
You were sitting in a
Light bulb.
chair.
let's go with
Wait, there's 4 ways to do this?
4.
Isn't that what he said?
Oh wait, maybe like flip it. That would make me
Yeah.
good.
If that counts.
Okay.
The answer is correct.
I'm gonna do this.
I can't wrap it. Like I'm trying to wrap it
This
around.
is a 2.5
This will work.
bad.
If I touch this,
Light bulb. 2.5.
and then I
Oh,
put this.
It's not like
volts
that.
is essentially like using
It's
the
just
sun.
that not
Which is
flat,
how
so it's hard to get
Yeah.
it.
Stay off the internet.
Let me just pull it.
He's messaging.
Yeah,
This is 1.5.
Oh my god, I lit it up! I lit it up!
Wire
Guys!
touched battery.
Literally doing the
If
same
it's
thing I
just
did.
something Rihanna can do it, then we're
I
Yeah,
already
that
tried that.
That works,
There's
right?
no way.
Okay, 3.
I literally, did you
Maybe
see
it's
my
one
number?
minute.
You're right.
We've done that like multiple times. And
Oh my god, his spinner's not here. Are you serious?
I don't think.
I did it, guys. I swear.
We don't believe you.
No, look,
This is literally-
hold on.
We
Hold
did
on.
Do you know how you did it though?
She's pressing it against the terminal like we already did.
We've been
She's doing the same thing
doing
we
what
did.
you're doing.
Hold on. I don't know what I did, but it
Were
lit
you,
up for
like,
like
put
1
one here?
second. I had it.
No.
Dude, what happened?
Look at exposed wire on my.
Spinner, I lit it up!
Alright, here's your first hint if you don't have it. The 2 sides of the battery are a potential difference. So probably that means that you should connect the 2 sides of the battery to each other. Number 2, if you've been doing that, you've probably been getting current, aka the wire has been getting hotter. Unless you have you guys have like a large wire, which probably means you wouldn't feel it as much about yours over there. If you are getting current, that's great. You're probably just not getting current where it needs to go. There's got to be a reason to go through the light bulb.
Mine lit up for like 1 second, Spain hour. I did it.
Last hint I will give you, and then you guys should all be able to do it, is this. The light bulb, electricity goes where it's easiest to go. It's like water, okay? So if you give it a path directly from one side of the battery to the other side of the battery, that's what it's going to take. And that energy is going to come out in some form, aka good job. How has that energy been coming out? Heat. So what a light bulb does, here is a general picture of a light bulb. One part of the light bulb is connected to the side and the other is connected to the bottom.
You said there was 4 ways to do this?
Yes.
4 ways?
Which are positive and negative.
Different
So
ways.
we're probably just.
Yes, and I'll talk about why.
We can put it on there.
See, I wrapped it around this
That's
so
what
that
we're
I
playing,
could
like,
get it, and then when I did that, it like.
We have it on this side, we have it on this side.
Did you get one yet?
No.
We can do it.
What if you just touch it?
Wait, let's see if there's something.
Then there's. You know,
Do what?
like just touch it with your ears.
It's never gonna be there because.
No, just like right there.
It's never gonna be there either. It's going around.
I don't even know. That's.
I assume it's only technically 2 ways, especially smart.
Jesus. Yeah.
So I don't know the second. You might not.
Yeah, that, okay, so it works on both sides.
See,
Trinity figured out
Oh.
what we figured out.
Oh.
Well, just you can touch it.
No, there's way 2 ways to do it. You just swap it.
I don't know. I'm proud of myself. I did it for 1 second.
How do you do it other way?
You guys got one
I get them in logic of the first one.
All right, here we go, guys. We're going to be done with that. Pay attention here real quick. So essentially, here's what they were, okay? The first way that most people get is this, right there, okay?
Yeah.
Why do you have to touch the side? Well, because if you touch the base, electricity is going to flow. Is there any reason that it should flow through the light bulb?
And then touch the side like this.
No, there's no. It's kind of like having. It would be like having like a water ride. Okay, like having like a lazy river here. Okay, here's a lazy river, and then there's a path over here. Would you expect water to move on this path right over here if it was connected to the lazy river? If there's no disconnect, probably not. It shouldn't. Water shouldn't be moving over on this outlet over here. So,
yeah.
shh, with me, please. Okay, so your basic circuit is this right here. Now, let's discuss why technically, not trying to be a but this one is a different one. Why is that? I'm assuming it's touching here. Yeah, literally, it's what does a positive and negative mean? Well, this is positive and this is negative, so it means charge is flowing the opposite way in that particular case. Okay, next, and the final two, I'll share with you. The last two are once again going to be flopped of each other. It's just this. In this particular setup, we touch the bottom to the battery and touch the side. So let's touch the side to the battery and touch the bottom. Check to see if it works.
I swear I think I did that.
Okie dokie.
Okay, so this is a basic circuit. Now, of course, we could add more wires to this. We could put other things in the setup, blah, blah, blah. But this is the schematic drawing based on what we talked about the symbols last chapter of what it is we have here. Okay, this is the battery. The long side is the positive side. And a light bulb is really just a resistor with a clear coating around it. So this is your circuit. One battery, one light bulb. What does this mean? Well, it means we have 120 volts. Okay, sorry, not 120. You have not in this particular case we didn't. Okay, we have 1.5 volts of a battery pushing in this particular case, And what does that mean? It is moving charge through here. And as that charge goes from the negative side to the positive side, it puts out 1.5 joules per coulomb. And how does that energy come out? Yes, specifically, arguably a little bit sound as well, assuming the light bulb was on. When the light bulb was not on, what did it come out as? Still comes out if you got current. Like if I connect one side of the battery to the other and take this out, I'm still going to get a flow of energy. So how'd the energy come out? Heat. It just got. Did it get a lot hotter in that particular case? Yes, it should have gotten a lot hotter if you connect one side of the battery to the other without the light bulb on, right?
Yeah.
Because all of the energy is going out to heat as opposed to some of it going to light and sound, and so you should get more heat in that particular way. So what I want you to think of is I want you to think of a wire, okay, as almost like a tube of water, okay? And when I look at, say, a flow of water, is it possible that a slower moving body of water could move more water? Yeah, it's just a real simple thing. Imagine that you go over to the Mississippi. Okay, is the Mississippi moving fast?
No.
Is it moving a lot of water? Yes. You walk over and you look at, say, a stream nearby. Could it be traveling much faster than the Mississippi? Sure. Is it moving more water than the Mississippi? No. Do we actually care about how fast the charge is moving? No. We just want to see how much charge moves in a certain amount of time. So if you're thinking about this tube, what you think of is a particular area inside the tube that the charge passes by. And how much charge passes by, we'll use little q, in a certain amount of time is known as current. Now this actually works with and it kind of helps for my understanding when I went through this originally, like the current of a river. Okay, the current of a river is related to velocity, but is not velocity. In what way would it affect the current if we increase velocity?
More water moving.
Or in this case, more charge moving past this particular area. If those charges going faster, then we're going to get more charge going past that particular section. Now, what should the units of current be? Coulombs per second is correct, but you know what? I don't like that, so let's go ahead and combine that to 1 ampere. So whenever you see something is at 2 amps, what you're really seeing is 2 coulombs a second is correct, yes. All right, now I feel like we can finally enter into the actual notes thing. Oh, I didn't do this. What are you messing with my multimeter? What's my multimeter? What's my multimeter? Wait, just turn up. All right, turn it. Okay, now. The letter they use for current, I apologize for this, it's not my doing, is the letter I. It's probably Latin. So current is the amount of charge past a particular point in time. And the reason why that's going to be particularly helpful for us is, as we discussed a minute ago, if you think of it like voltage being an empty hill, okay? This is voltage, okay? What did we need to figure out how much energy is going to happen in a certain amount of time? We need to know how many children per second, coulombs per second, current. How much current is going to need to pass by that particular spot? Would you know? All right. Now, one thing that you'll notice up here is that you only see positive charge. There's about 3 different types of current or understandings within current that you got to get to. Okay. The first one is, well, I don't think they're going to talk about it later. They might talk about it later. It's definitely in the reading. Okay. Actual current conventional current, and this is just another idea that goes with those two, drift velocity. So actual current, as the name suggests, is the way that current is actually flowing. And for the most part, what charge is it that usually moves? Almost always it's going to be the negatives. I say for the most part because there are certain instances where you are dealing with, say, like ions, like positive ions that you've created, like over in chemistry. And if I move positive ions to the right, yep, they're going to the right. So actual current is, as the name suggests, actually the way the charge is going. Conventional current, though, is the one that we're going to use, and the one that all of science uses, and the one that all the world uses, and that is the flow of positive charge. As you're seeing on the screen right now, we have a bunch of positives going. What are you doing? I didn't want to. Okay.
I stands for current, right?
I is current, yes. There you go. I average is defined as the change in charge over time. The SI units are coulombs per second or ampere. Now I'll cover these other two. I think that they do talk about them in just a second. So if you look at conventional current, it can get into calculus and limits and all that sort of fun jazz. This kind of goes back to, you remember how we talked about instantaneous velocity and average velocity? And I told you that instantaneous velocity is actually a calculus limit. It's the limit. We'll talk about that if we get into the calculus part a little bit later on. But it's the same type of thing here. Average is delta Q over delta T, just the same way that average velocity is delta X over delta T. When does it matter? The average versus the constant versus the changing. Literally what I just said, when it's constant versus when it's changing. And we're almost never going to have to deal with the second one in this class because pretty quickly it will get up to its particular average. All right, so this is what I was going to talk about just a second ago, and that is conventional current versus actual current. Here's the deal. In the right picture, you see that negatives are moving to the right. Isn't that the same, though, as left. All right, I did it backwards because of my direction. Okay, moving to the left. Isn't that the same, though, as positives moving to the right? Well, mathematically, let me show you that real quick. Let's say, keep them for right now, okay? Let's say, for instance, we have a charge over here of positive 12 coulombs, okay? And actually no, I take back what I said. Let's go negative 12 coulombs. Negative 12 coulombs, all right? And over here, I'm gonna move some charge. How much charge do I want me to move?
7.
What's that? So let's move negative 7 coulombs, okay? And originally we'll say this was, I'm just making up numbers here. Let's go, originally it was negative 5 coulombs. All right, so imagine it's negative 12, it's negative 5. I don't like that. I don't like that at all. I'm wrong. Let's go negative 15 coulombs. All right, so forget this number for a second. There's negative 12 here, there's negative 15 over here, and actually that wouldn't be the way it would usually move. It would usually move the other way, so I'm gonna make it the other way. Sorry. All right, now, this is in process. So if negative 7 coulombs leave over here, what charge should this be now?
8.
Negative 8. Okay? And if negative 7 coulombs come over here, what should it be? Negative 19 coulombs. Isn't that the same as positive 7 going the other way? If positive 7 leave this, what happens to its charge? It would decrease. In other words, you can kind of think about this is negative 12, and over here I'm going to put a positive 7 and a negative 7, right? So if positive 7 leaves, now it's negative 19. Does that make sense? And if positive 7 goes over here, now it's negative 8. So 7 bigger. I don't know why I did the negatives. I think that's kind of confusing. Let's go to positives real quick. Let's try this again one more time. Just make sure we're good. Let's go 12 and 15. How much charge do you want me to move? Pick a number. No, we need to do 7.
8.
2.
2. Let's go negative. Let's move positive 2. So I'm going to go positive 2 is going this way. So what charge should be on that now? 13. What charge should be over here now? 14.
Oh, wait, 14, sorry. Thought we were moving
That is the same as negative 2 moving the opposite direction. Because if this is negative 2 plus 2 and negative 2 just left,
I thought it was illegal to think of like positives moving.
it's not illegal. It's not illegal. Do positives actually move? No, not usually. That being said, mathematically, wouldn't it be nicer if they did?
Yeah.
Yes. So, conventional current says, let's be nice to ourselves mathematically, since statistically it's going to work the same way, and this is really all about energy anyway, right? If negative 1 coulomb goes from the negative side to the positive side, it's going to get outlet 120 joules. If positive 1 coulomb goes from the positive side to the negative side, it's going to get 120 joules, right? So we're really dealing with energy anyway. So conventional current says the other nice thing about to show you about conventional current is this. If I go back to this circuit right here, which way would the actual current be going in this circuit? Clockwise or counterclockwise?
Negative. So, clockwise.
I don't remember.
Counter. Which side is the positive side of the battery? The big side.
Oh.
So this side is the negative, and which way is actually flowing? The negative charge. Right? So that's the way current is actually going. When you guys were messing around with your circuit, was it really obvious which way the current was going? I would argue no. You saw energy, you felt energy, it's going, you're not going to notice it at all. So what we do then is we go, all right, come on, go back. What are you doing? All right. And we say, all right, conventional current is clockwise. The other nice thing about that is also the direction of electric field. Leaves a positive, goes to a negative. So conventional current is just the flow of positive charge. Does positive charge usually actually move? No. But which way is conventional charge going to go relative to actual? The opposite way, and it just works the exact same way. Does that make sense? Okay. Last idea that I told you that I wanted to cover was drift velocity. Okay. 10 amps, as you would imagine, is a lot of current. How do you know 10 amps is a lot of current? 10 coulombs per second, as we discussed previously, 10 coulombs is roughly how much charge is in a single lightning bolt. So it's a decent amount of charge. Okay. A copper wire flows electricity pretty darn fast. If I have 10 amps in a copper wire, I'd like you to, real quickly, 30 seconds to a minute, make a guess at how fast, no, let me say that differently. How much velocity an electron in a wire is traveling at. Just make a guess. Just guess. So you've got a wire here. Okay, imagine a wire's running across. I got 10 amps of current going through it. The question is, what is the velocity of an electron in that wire? Just guess. I'll go around and ask for a guess of each group before we continue. Get an answer. Here we go. What you got? Make a guess. Make a guess. Make a guess. Number. You said fast. Pick a fast one.
1,000.
Meters, child. Per second. Meters per second. 1,000 meters per second. What do you say?
10 to the 6 meters per second.
Okay. What you guys got? All right. What do you guys? What do you guys? What do you have? What do you say? I thought I had you guys join in. Just join in permanently. Suck to suck. I'm over here. What do you guys got?
A million
Nick?
megameters per second.
It's 1 millimeter an hour.
What?
Hang on.
Notice I purposely, it was not an accident that I changed the words at the very beginning. The first thing I said was how fast is it going? And I said, you know what? No. What's the velocity that it's going at? Why are those different?
It's gonna pass.
Velocity is a vector. Velocity has to do with displacement. Are the electrons probably going fast? Yes. Why aren't they moving nearly that quickly through the wire? How many electrons do you think are in that wire? I know I talked about it being water. I'm going to use a different analogy. It's the world's most insane bumper car / traffic jam that has ever existed. If all of the cars in the traffic jam were completely fine running into each other at full speed and always attempted to go full speed every single time, why doesn't an electron go very fast?
They slow each other down.
There's other electrons in the way. So in truth, what actually happens in a wire probably looks something more akin to this. See, I draw this in what you random yellow line. All right, I draw this and you think, oh, it's an empty tube. No, that tube is full, jam-packed, full of charges. So this little guy right here doesn't go like that. Okay, that little guy in there goes like, oh, come on, you got this. Okay, this. And velocity is displacement over time. So, are the charges moving fast?
Yeah.
Yes. Along that path that I just showed, they are probably traveling in some of the numbers that you just said. I think it's either like 10 or 20,000 meters per second, that type of deal. They're going very quickly. But if you tracked a single one in the wire, does it have a large velocity? And that makes really, really good sense, because if they did have a large velocity, I would imagine you would be able to look at a wire and see it change because of how much charge is moving through it. As it stands, if you look at a wire, do you expect to see any change at all just because current is traveling through it? No, it looks exactly the same, which means almost no percent of the mass is actually moving through it. There's not that much. So it's moving stupid slow. So how on earth could it be moving a considerable amount of charge if it is moving so incredibly slow? How can the Mississippi move an incredible amount of mass even though it's moving slower than the stream next to it? Area. And there's a lot. I mean, and a lot doesn't even play. How much charge do you think is in a wire? There's an insane amount of atoms that are in there. You don't need to move very many of them to move a considerable amount of charge. Even though we said that for a copper wire, it was moving at 1 millimeter per hour, we were moving 10 coulombs per second. How can we be moving so much charge? Well, there's a lot of charge jam-packed into running through that particular area right there. Does that make sense? If it will, think of it like this. If I said a traffic jam, imagine a traffic jam with 20,000 lanes. Does the traffic jam have to be moving quickly to move a lot of cars past a particular point? No, it doesn't. All right. So in this particular picture right here, we have obviously positive moving right. That's conventional. And the left, we have negative moving left. They are equivalent. Notice in both arrows pointing to the right underneath. Or in this particular case, here's another way of putting it that I kind of like what they do. Okay. If you imagine the negative moving left, the negative came from, let's say, a neutral area. Okay, like imagine that you have, well, actually, like there's a lot better than mine. So let's say this. We got positive and negative, and positive and negative, and positive and negative. So it's neutral, yes? So if the negative moves left, did the positive move? No, but it's sort of like the positive just went right. So, and the way they put it is this: temporary positive holes or atoms in the conductor are moving to the right. If the negative move left and they vacate that area, what charge is that area now? Positive, so it's like positive moving, right? All right. So the energy of a charge, we've discussed this a bunch of times, is going to be voltage or energy per charge times that amount of charge. The energy in a wire is going to be just the opposite of that. Okay? And we'll talk about that more in a second. So look at the pictures below and rank them in these regions from the lowest current to the highest current. Assume that all of those charges have the same magnitude. So discuss quickly in your group which of those have the highest current and which of those have the lowest current. Also be able to tell me when you're done what direction that current is in. So we're going from lowest to highest.
Wait, is D just two negatives going together? Okay, I couldn't tell.
Because they should be going in different directions. That's how the work. Would they not?
All right, what's the most current? Sorry, what's the least current?
D.
D. Which direction is that current in? Notice when I talk about ranking them for you guys, I'm not worrying about left or right here type deal. So why is D the lowest? -2. And so therefore, which direction is the current on D? And when I say current from this point forward, I mean conventional. Every time I say current, I am assuming you're talking about the positive flow of charge. So what is the direction of current on D? To the left. Yes. Okay. What about what's next? B should be next. Okay. Because it is. And what is the direction? That should be easy. What's the direction of current on that one?
+3 to the left.
But just to the left. It's fine. Okay. All right. Next is.
A.
Next is
wait,
C. Okay, now I heard what some of you guys were attempting to do in canceling out the positives and negatives. What I want to address here is that if a negative moves, let's look at C real quick. If negative moves to the left, left, I'm backing this up, what is that the same as? Positive moving to the right. So you got the right idea with them canceling, but let me show you what the picture looks like if they're going to cancel, and I think it will make really good sense. If I had drawn another circumstance here, like this, if positives and negatives were in fact going the same direction, this negative would be as though the positive were going to the left, and therefore what's the current in this picture? Zero. Current in this picture is in fact zero. Yeah. No, it's not feasible. It's more of a hypothetical. So yes. So C should be next at 4 charges moving what direction?
Right.
To the right. Okay. And finally, of course, A is the most with 5 charges moving which direction? Also to the right. Please notice that the direction of the charge in this case, D was left, B was left, C was right, A was right. The direction of current did not affect, of course, the magnitude of current that we were addressing right here. All right, so I've actually already talked about this, but I think they're going to do some math that goes along with this and chart to show you kind of how this stuff gets put together. Yeah?
Why do having more charges in it make it faster? I thought the charges would slow
No. I didn't say having more charges in it would make it faster. Speed is not up here. Hold on. Make sure we're addressing this. What that said in that particular setup is that these were the charges moving in about, I don't know if they said, the assumption here is that all of these are moving past this area in the same amount of time. Having more charges does not, well, actually, this is perfectly with what we're doing. So I'm going to do the math, essentially showing you the equations of creation in this particular case. So here we have a section of wire, okay? we have a section of wire, and these charges are going to go by here using drift velocity. So how much distance are they going to cover? Simply the drift velocity times time. AKA, if I knew that the wire, they went 1 millimeter an hour, it was 2 hours, obviously they would go 2 millimeters. That's what that equation right there says, although that's not going to be helpful. Okay, this equation right down here says the total charge should be equal to this little n right here, I believe represents, yeah, this guy right here represents charge density or charge per volume. What would decide charge density about something? What's that?
How much charge goes per?
Right, that's what it's defined as, charge per volume. But what would decide that about a particular material? Literally what it's, yeah, so you're getting a little more complex. Just the material is what I'm going for. Whatever material it is would decide this, and the density of the other said material. So here I have density of charges per volume, and I'm multiplying by, what is this right here? Volume. So this is telling me, what's it telling me inside this particular parentheses? As the number of carriers. The number of children, sorry, carriers. The number of carriers. So why am I multiplying by Q? That'll be the charge per carrier, which is usually going to be elementary, yes. E, charge of an electron or proton. Okay. So you have here that the distance that it's going to cover is equal to the velocity, the drift velocity times time. Yes? So I can do a little bit of substitution here with that previous equation, and I can substitute in for delta x this VD delta t. So now I've got this new equation for delta Q. It is the charge density times the area times the drift velocity times time times the charge itself of an individual. And now we can define current in a different way. I'm just going to take this equation right here, and I'm going to divide delta T on both sides. And what is delta Q divided by delta T? Current. Now, this equation over here on the right side should make really good sense why all of them are there. Now, you should be able to construct this equation. I don't think you're going to have to use this equation a ton on your homework, but you should understand all of it. Basically, why should current increase because of each of these? Why does it make sense that charge density should increase current? Yeah, imagine the Mississippi versus now the Mississippi is full of molten hot iron. You're going to get more molten iron at the same velocity, more stuff through because it's simply denser. Does it make sense that the actual charge on each of those carriers should probably have an effect on how much charge moves through? So this is how many carriers per volume. Does it make sense that the drift velocity right here would have an impact on how much charge goes through? AKA, if I double how fast the current is going, should it double how much charge comes through? Yes. Even though that's a small number, it does in fact have an impact. Okay? Does it also make sense that the area of the wire itself should affect this? Absolutely. Now I'm going to tell you that tomorrow we're going to get into a much easier way of tackling this. Okay? Like I said, you're not going to mathematically have to tackle that too much, but I do want to make sure that you understand how we got there. So, and there's drift velocity in a nutshell. Kind of drew it a little bit earlier. What does an electron do? It bounces around. Even though their speed is incredibly high, their average velocity or drift velocity is relatively small due to collisions with all sorts of atoms being momentarily and sharp and changing what direction they're in. Like I said, think about a car in the world's worst traffic jam of all time, and you have an idea of what an electron does specifically in a wire. Don't worry about that right now. I won't do that yet. I'm going to do Ohm's law. All right, I don't like how they do Ohm's law, so I'm going to talk about it real quick. All right, imagine you've got this. Imagine that we make, actually no, we'll go back to this guy. 2 more things and I'll be done for today. This guy's first. All right. This is how we make measurements about a particular circuit. The circuit that you're looking at right here is 100% the circuit that we just did a minute ago. Light bulb, battery, and yes, we have some devices being measured along that particular way. The two things that we use to measure in this are a voltmeter and an ammeter. Name kind of sort of makes sense that an ammeter measures amps, aka current, and that a voltmeter measures volts. Okay, I'll come back to like exactly how they do that, actually not in this chapter, later on. Their methodology for working actually is based in magnetism, so we have to kind of take a step back here. But let me ask you a question. I'm going to put a ratio up on the board. Delta V over I. What would it mean about a material if that ratio was incredibly, incredibly high? What would it mean about a ratio? What would it mean about a material? If I make measurements of said material, I use a battery or a Wimphurst machine or whatever to get voltage, and I somehow measure the current, what does it mean about that material if that is really high?
There's a lot of battery, but there's not a lot of current running.
So you would say that that material is what? Not very good at. So you'd say it resists. So it's an insulator. It's 100% an insulator. Yeah. And what would it mean then if that ratio was very, very low? So that would mean ultimately, let's do it mathematically. I mean, you're on the right idea. But let's go back to what does it mean numerically if this is high? Voltage is really big. Not very much current, right? So I'm with you. Makes sense. It would be an insulator. What does it mean if that ratio is very, very low? A lot of current, not very much voltage. So you would imagine, like you said, that is a conductor. This ratio that I just drew on the board is known as resistance. Resistance, this is an important thing. This goes right kind of back to capacitance. Resistance itself is not a reason why it does it. It is a mathematical ratio. The actual units, this is very important, the actual units for resistance are what? Correct. Remember that. Resistance is a ratio between volts per amp. If I say that I have a resistance of 100, what am I saying? What's that? You're right there. If I use 100 volts on this material, you get 1 amp. Okay? That's okay-ish. That's all right-ish. Now, I wanted to remind you of this, that it is actually volts per amp before they put up what its real units are, because you've probably heard the real units before, and I don't want to make it too much easier on you. The actual units, volt per amp, is known as an ohm. So if you see that a material has 100 ohms of resistance, what it's really saying is that material takes 100 volts to get 1 amp. Our skin is the most resistive material on us. Okay? Our skin probably runs at 100,000 ohms, or it would take 100,000 volts to get 1 amp flowing through my skin. Now, because of that ratio, this kind of works very similar to capacitance. Capacitance was the ratio between charge and voltage. Resistance is the ratio between voltage and amperage, meaning if I know one, then I automatically know the other. So, for example here, I said that my resistance is of my skin is 100,000 ohms. So do some math for me real quick. Shouldn't take you that much. How much current should you get if you put 1.5 volts across it? Do the math real quick. You can do it in your head, do it in your calculator, I don't care, but do it. Okay, give me a number. Your skin, 100,000 ohms. You put a 1.5 volt battery across it. How much current do you get? What do you got? It's very small.
Oh, good. 0.00015.
Now that should make sense because for it takes 100,000 volts to get 1 amp. I only gave 1.5 volts, so it shouldn't have very many amps whatsoever, right? Which makes sense. Our skin protects us from current and a lot of other things, but there we go. There you go. You got a 120 volt battery, okay? You want 6 amps. There's 20 ohms in that particular case. Yeah, we'll talk about that in the actual lab. Don't want to talk about that yet. Come on, where's that? Power is what I want to talk about next because that's where I began. Because I began today. Now, the conversation is really easy with power. What is power by definition? How much energy in a certain amount of time. Now, the equation for power is confusing because you can change what you use for energy. We've done Q over time, right? We have done work over time. In this particular case, it's just energy over time. If you want work over time, that's completely fine. Well, we did this at the very beginning. We want to control how much energy comes out of a particular circuit. What does voltage tell us? How many joules you're going to get per coulomb. So if you want to get to joules per second, you got an empty hill full of a bunch of potential, a possible amount of energy per child, coulomb. What do you need to know how much energy is going to go down per second? Coulombs per second. AKA, to get power, you need current times voltage. Give me a standard power of a light bulb that you use in your house. 40 watts is usually in the living room. You can get 120 watts, of course, out. Usually those are going to be in the garage. Other standard ones, 60 watt light bulbs are fairly standard. They're a little bit more in between the two. You're probably not in the living room at that time. Kind of a brighter area, might use 60 watts. Totally up to you and what you decide. Does the power company actually decide how much energy is coming out of those? No. What do the power company actually control about a light bulb? No. The voltage is set at 120 in America. So what does the power company actually control about the light bulb? What's that? No. Resistance. The resistance of the light bulb. See, watch here. We know, the power company knows it's going to be plugged into 120 volts. Yes? So, what does that mean has to be true of the current? If I want 120 watts, 120 volts, what has to be true of the current going through it? 1 amp. And since resistance is the ratio between these two, what does the resistance of the of the light bulb have to be in order to pull off 120 watts? 120. 120 ohms. Okay? Let's try again. One more, and then I'll be done for the day. What if you have a 60 watt light bulb? Calculate for me what is the resistance in a 60 watt light bulb.
You said the resistance.
The resistance of a 60 watt light bulb. What'd you get? 240. Here it is in a nutshell real quick. You're welcome to do the math that goes with it. If that's 60 watts, and that's 120, which it always is in America, okay, what does current have to be? 0.5. Yeah, 1/2.
Wait, so
That's 120, and you only want a half amp out of it. What's your resistance have to be? 240. Now, again, the electric company is assuming that 120 volts are going to that. Is that fair every outlet in America? Most part, yes. Do you know what it looks like in an outlet if it's not 120?
Yeah.
Has a different shape. Literally has a different shape. That's why they use the shapes, so that you can't, unless you're an idiot, attempt to force a different shape into the other shape. If you see a different shape, like for example, if you go down and you look at your washer and dryer, some of those will in fact actually have normal outlets. They run on 120. Okay. Some of those will have those like different, like you've seen those kind of like the screen faces. Okay. I can't remember what voltage they are, but they're different. And if you were to go over to Europe, what do you notice about the shape of outlets there?
It's different.
They're entirely different. So never try to force your outlets into the wrong shape, and you're golden. Just don't be an idiot. Now, what is the problem? Excellent question. Does anybody know the difference between the voltage in Europe versus the voltage in America?
No.
Voltage in America is 120. The voltage in Europe is 240.
Oh goodness.
What does that mean is the difference between them?
Double.
For 1 coulomb of charge, you get twice the energy. Well, that sounds great, except if you're running, say, oh, I don't know, your cell phone, and it's used to 120, and it gets 240, it doesn't get twice as good. It gets twice as much energy. And we learned this in thermodynamics. Where does extra energy go? Heat. And too much heat in a confined area is one of two things. Either one, bomb, okay? Or two, best case scenario, it heats up a wire so much that that wire melts and currents can't get through there anymore, and your device simply doesn't work because it's heated up. So if you plug your out stuff in over in Europe, boom, very quickly. Don't do it. But like I said, as long as you're not an idiot forcing a wrong shape into the wrong thing, you're golden. Don't worry about it.
Wait, so hold on. So what's the difference between the plugs that only have like the two things and the plugs that have like the three little pegs?
Ooh, that was almost. Yes, that is true, and we'll talk more about grounding a little bit later. Most of them made anymore. I don't know if you're going to find too many. I don't think you're going to find too many standard just 2 plugs anymore. Most everything is going to be grounded. But.
No, like not the actual outlet, like the ones that you plug in.
I think it's just like a
What's the
safety
adapter?
Oh.
to like
What's
if
out
there to
What's
be
the
able to
adapter?
access like
A robot in disguise.
sorry, charge
It's a transformer.
out or something. something goes
Transformers
wrong,
are
it's just-
means that actually we use them all the time. Not all electronics want to be running on 120 volts. So if you've ever seen, just get a Chromebook charger real quick. Yeah, if you've ever seen basically anything with a box on it whatsoever,
It's hot.
that's a transformer. It changes the voltage from 120 to something else. Chromebooks aren't that powerful. They don't want a ton of voltage on it, so this is a step down transformer. It will make it lower. So the box that you put on there is done it. But that being said, you do that with your cell phone already. You don't plug in directly to 120 volts with your cell phone. There's a box, and that little box actually also steps the voltage down, which is why if you plug that guy into your computer, you don't gotta use a box because your computer actually can read how much voltage is specifically needed by how much voltage is used by your particular device, and will actually put out that amount of voltage so that it can be used. What's up, Jake?
What do you do if it's needing more than 120?
You have a step-up transformer.
Oh, that's a thing. How does that work?
Magnetism. We're not there yet.
What uses it?
What's that?
What uses a step up?
You see transformers on power lines all the time.
Bridges?
No.
No.
You see those? This is not. There's other things that are up there. You see those giant cylinders that are like on the top of like power poles sometimes? Many times they're almost always step down. Almost always it's step down because it's easier, it's more efficient, it's a lot of things. But there are cases where I need more voltage. I was going to say that a lot of stuff that needs a lot of energy at the beginning might, but that being said, they usually just use capacitors. So like you see that little green thing on top of my thing over there. That's it's a simulator of essentially what runs Mr. Freeze. Shoots rings up in the air. We'll talk about it when we get to electromagnetism. But that might use a step up. A lot of times transformers are on the outside. You see them in boxes, but there are quite a few larger electronic devices that can fit the transformer inside the device itself. As a matter of fact, I remember, this is aging me here, but I remember when, I think it's Xbox One, and it might have been 360, I think it was Xbox One though, when they were talking about it, there's a decent amount of conversation about putting the transformer actually inside the box. That would have made it that much bigger though, and more bulky, and it looked sleek the way it was, and so almost always they regularly decide to take the transformers and put them out separately. But that would have made it more, I guess, not compact, but you wouldn't have that box outside because of the main. Other questions? As always, start the homework early. I'll check tomorrow to see how many of you have started the homework early. And yeah, do the reading. Any other questions?
Can I come listen to that?
Yes, you guys are always welcome. I was very surprised last week that I did not see very many of you at 7th hour physics, given that the next day was your chapter 16 test.